Hi, everybody. Welcome back. This is Ms. McClellan here to go over note 7.2.1 with you, basic probability rules. Okay, so we start out with just an overview of randomness. Rock, paper, scissors, coin tosses, the lottery, casinos, games involving dice, spinners or cards, even traits that we inherit, such as gender, hair and eye color, blood type, dimples, all are determined by the chance involved in which genes get passed along. Now, all of these represent chance behavior. We can understand and work with. The outcomes are governed by chance, but in many repetitions, a pattern emerges. We use mathematics to understand the regular patterns of chance behavior, and this is called probability. Probability. Now, chance behavior is unpredictable in the short run. But it has a regular and predictable pattern in the long run. And there are two types of probability to describe chance. We have empirical and theoretical probability. Now, empirical probability is based on actual observations. So if you flip a coin 500 times and you get heads 489 times, the empirical probability would be 489 out of 500 for flipping heads. That's empirical probability. Theoretical probability is empirical probability, but based on an infinite number of actual observations of trials. So for example, we can't flip a coin an infinite amount of time, but we would expect out of an infinite number of flips, half of them would land on heads. So the theoretical probability for a heads or tail coin flip would be 0.5. Let's look at some probability terms. These are all terms we learned earlier in the year. Random event. That's an activity with some measurable result. Outcome. That's the result of one trial of one random event. An event. That is a set of related outcomes. A sample space, that is the set of all possible outcomes. And that's usually just called S. All right. And we have our classic probability formula. The probability of an event is the number of outcomes in the event divided by the probability of an event, is the number of outcomes in the event divided by the number of outcomes in the sample space. So in this formula, all outcomes of the sample space aren't equally likely. And we say in notation, P of E equals number of outcomes in the event divided by the sample space. And that's not totally accurate because I should really be saying the number of outcomes in the sample space, but this is usually how we would write it. Okay, next page. And we have an example. So in this example, we have a bag and it has 10 marbles in it. 2 of them are black, 3 are blue, 1 is red, and 4 are white. 2 black, 3 blue, 1 red, and 4 white. What is the probability of pulling out a black marble? Well, that can happen 2 ways out of a total number of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possibilities. 2 out of 10. And you might want to write that as decimal, 0.2. What's the probability of pulling out a red marble? Well, there's only 1 red marble in the bag, so our numerator, the number of outcomes in the event of pulling a red marble, is 1 out of the number of items in our sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Still 10. 1/10. This is 0.1. Next problem. This is a classic problem. 2 die are rolled, and the sum of the pips noted, those little dots on a die, are called pips. Did you know that? So if I rolled a 5, it would look like that. Anyway, what is the probability that a sum of 9 is rolled? So I'm going to draw our sample space here. And on top, I'll show what happens with the first roll. And on the side, I'll show what could happen on the second roll. Okay, 1, 2, I could roll a 3, 4, a 5, or a 6. And I could roll 1, 2, 3, 4, 6. And the sample space will consist of all of the sums. Okay, so if I roll 2 1s, I'd get 2. If I rolled a 1 and a 2, I'd get 3. And these just want to separate. I'll just fill it in. 4, 5, 6, 7. I'm adding them. So if I roll a 1 and a 2, the total is 3. And then it increases by 1. Okay, so this is the sample space. The interior of this area is the sample space. It's all of the possible sums I could end up with if I rolled 2 die. And all of the ways that I could get them. So this question says, what is the probability that the sum is 9? Well, sample space is 36. So my denominator is going to be 36. And how many ways could I get 9? If I rolled a 6 and then if I rolled a 3 and then a 6, a 4 and then 5, a 5 and then a 4, or a 6 and then a 3, all of those would result in rolling a 9, and there are 4 ways that could happen. So the probability that I get a sum of 9 is 4 out of 36, or 0.1 repeating. Next example. A coin is flipped 3 times, and the results of each flip are noted. Let's draw the possible outcomes. Now, earlier in the year, we were drawing tree diagrams, and I think that that really confused us. But when outcomes are equally likely, we can actually get away with just making a list. So I'm going to flip this tail 3 times. Okay, I could get 3 heads. I could get 3 tails. I could get 2 heads and a tail. I could get a head, a tail, and then another head. I could get a tail and then 2 heads. I could get 2 tails and then a head. I could get a tail, a head, and then a tail. I could get a head and then 2 tails. Is that all the things that could happen? I think so. All right. So this is going to be my sample space. And notice there are 8 elements, so S equals 8. And I want the probability of exactly one of the flips resulting in a head. So how many ways could I get just 1 head? If I rolled a head and then 2 tails, that would work. If I rolled a tail, a head, and then a tail, that works. And 2 tails and a head, and then a head would work. So there are 3 ways that could happen. So the probability of exactly 1 head equals 3/8. Or if you prefer in decimal form, 0.375. And I'm using a calculator to get my decimals. Next question is, what is the probability that at least one of the flips results in a head? So now I need to know probability of at least 1 head. And that's not the same thing, because I could get just 1 head. I could get 2 heads. Or I could get 3 heads. The only thing I can't have is 3 tails, because I just need at least one of them to be a head. It's okay if more than that are. And that probability is 7/8, because except for one of the 8 results in at least 1 head. In decimal form, that would be 0.875. Some of you may have done this problem a little bit differently. You may have done 1 minus 1/8 to get 7/8, and that's great. That's called using the complement, and it's something that we will be defining and practicing shortly. Probability definition. So the probability of any outcome of a chance process is a number between 0 and 1, where 0 means the event will never happen, and 1 means the event will always happen. And that number represents the proportion of times an event would occur in a very long series of repetitions. Hopefully you can see this a little bit better. I just paused to change the lighting. I know the production quality is not super great. Anyway, we continue. The idea of probability seems straightforward. It answers this question of, hey, what would happen if I did this a bunch of times? What would happen if I did this many times? Now, we've said that randomness is predictable in the long run. Unfortunately, this still doesn't look good. Maybe that's better. Unfortunately, everybody, our intuition wants to tell us that random phenomena should be predictable in the short run, but that is very wrong. In fact, it's something called the gambler's fallacy. So there's this myth of short run regularity, and it's the idea that probability, that randomness is predictable in the short run. And it's really important to know that that is incorrect. So this is not true. The myth of the law of averages is not true. Probability does not allow us to make short run predictions. It tells us random behavior events, how random behavior evens out in the long run, but future outcomes are not impacted by past behavior, by past chance behavior. Just for example, in a game of a coin toss, you might get 5 tails in a row. That does not increase the likelihood of getting ahead on the next flip. The probability of getting heads remains at 50% for each individual flip. Okay, basic probability rules. The probability of any event is a number between 0 and 1, as we've said. The probability of an event is the long run proportion of repetitions on which the event occurs. All possible outcomes together must have probabilities that add up to 1. And that's because you're sure something's going to happen. Otherwise, there wouldn't be a measurable outcome and you wouldn't have a random event. Okay. So the probability that an event does not occur, this is the idea of complement, is the complement. And it equals 1 minus the probability that the event does occur. And when we refer to the event, not A, it's the complement, and we write A to the C. Sometimes we might write A prime. Both of those mean complements. And in this situation, the probability of A, actually always, is equal to 1 minus the probability of the complement of A. And similarly, the probability of the complement of A is equal to 1 minus the probability of A. Mutually exclusive. If two events have no outcomes in common, then the probability that one or the other occurs is the sum of their individual probabilities. When two events have no outcomes in common, we refer to them as mutually exclusive. For example, the probability that today is Monday and the probability that today is Tuesday are mutually exclusive because I cannot be both days at the same time. In other words, the probability that I am both Monday and Tuesday is 0. I can't be both. I'm one, I'm the other, or I'm something else, but I can't be both. Here's an example relating to mutually exclusive events. Imagine rolling 2 fair 6-sided die, 1 red and 1 white. What is the probability of rolling a sum of 5 or 2 even numbers? So I'm going to circle in, this is this pretty silver pen, I will circle all of the ways that I could roll a sum of 5. Here's one. Oh, you really can't see that. Can you? Maybe a little. Well, it's not perfect. Oh well. There's another way I could roll 5. Another way. And another way. That's all the ways I could roll 5. Let me just try to make it a little more obvious. Okay, so the probability of rolling a 5 is equal to 4 out of the size of my sample space, which is 36, because there are 36 things that could happen if I roll 2 die. And the probability, I want sum of 5 or 2 even numbers of rolling 2 evens is, I'll highlight the ways that I could get 2 even numbers with yellow. Okay, so if I rolled a 4 and a 6 and a 2, that's 2 evens. 6 and a 4, 2 evens. 6 and a 6, 2 evens. 6 and a 5, no. Okay, so it looks like it's going to be every other, and I can just follow a pattern. And it looks like there are 9 ways that I could roll 2 even numbers. So the probability that I roll 2 evens is equal to 9 out of 36. And the probability that at least one of these things happens is going to be their combined probability. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the probability that I roll 5 or 2 evens equals 13 out of 36. Now notice that there's no way to roll a sum of 5, and get 2 evens. That means that these events are mutually exclusive. I can't have both even and roll a sum of 5 at the same time. Therefore, these events are mutually exclusive. Period. And mutually exclusive events are nice because it's really easy to find the probability that one happens or the other. So if you have 2 events, 4 events, A and B, if they are mutually exclusive, and this is only true if they're mutually exclusive, the probability of A or B equals the probability of A plus the probability of B, period. And we saw that up here. 13 is 4 plus 9. And as always, if you want, you can write this as a decimal, this answer up here. So 13 divided by 36, I'm doing it on a calculator, is equal to 0.361 with the 1 repeating. Next page. Okay, example 2. So online courses are rapidly gaining popularity among college students. Maybe some students in college just like online school after COVID. I don't know. Anyway, we randomly select an undergraduate student who is taking an online course for credit, and we record that student's age. Here's the probability model. So the age group could be 18 to 23, 24 to 29, 30 to 39, 40 or over. And the associated probabilities are 0.57, 0.17, 0.14, and 0.12 respectively. We want to show that this is a legitimate probability model. And that just means we want to show that all of these probabilities add to 1. So let's check. Do all the probabilities add to 1? Question mark. Well, we have 0.57 plus 0.17 plus 0.14 plus 0.12 equals 1. Yay. Yes, it is a legitimate probability model. On to part B. We want to find the probability that the chosen student is not in the traditional college age group, which is 18 to 23 years old. So we want to find the probability that we are not this. So the probability that somebody is not 18 to 23 is going to equal, and there's 2 ways to do this. I'll do this the direct way, and then I'll use a complement. It equals 0.17 plus 0.14 plus 0.12, which is 0.43. But notice, you could just use the complement. By saying 1 minus the probability, 1 minus 0.57, 1 minus the probability that somebody is in the 18 to 23 age group. And that would also get you 0.43. Probability of not 18 to 23 equals 1 minus the probability of 18 to 23. That is the idea of complement. And it's useful because it usually results in far fewer computations. Next example. Imagine we rolled 2 fair, 6-sided dice, 1 red and 1 white. We're revisiting this model. What is the probability of rolling a sum of 6 or 2 even numbers? Let's think. Why are we asking this question? What do we have to gain from this? Come with me on this journey. All right, let's find these probabilities. I'm going to, let's see if gold shows up better. Is that better? Ooh, it is better. Okay, I will circle the ways I can roll a 6. Here's a 6. Here's a 6. Here's a 6. Here's a 6. And here's a 6. So I want the probability of rolling a 6, and I'll do the next part in yellow, 2 even numbers. How is this problem different than the last problem is the question I hope you're asking yourself. let's highlight the even numbers. Okay, so there are 9 ways to get even numbers and 1, 2, 3, 4, 5 ways to get a 6. And naively, I might think that all I have to do is add those things together because that's what we did last time. So let's see, is the probability of a sum of 6? Well, that's going to be 1, 2, 3, 4, 5. That's 5 out of 36. And the probability of 2 evens, well, that's 9 out of 36. I counted last time, but I'll do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9. And can I say that the probability of sum of 6 or 2 evens equals 5 over 36 plus 9 over 36? Let's see. So that would be 14 over 36. And let's check if it's right. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is strange. So this is wrong. No. And why is that wrong? Well, I'll show you. The probability of sum of 6 or 2 evens is, this is part of the story. It's got 5 over 36 plus 9 over 36 in it. But look, when I counted this 5, 1, 2, 3, 4, 5, I also, I was double counting these pieces that are both adding to 6, but using 2 even numbers to do that. And because I counted those twice, I ended up with 14 out of 36 instead of 12 out of 36. What I have to do is I have to subtract the number of elements in the intersection. I have to subtract the things that I double counted. So I'm going to subtract 2 out of 36 because that's how much I overcounted. And that equals 12 out of 36, which is what I want it to equal because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I miscounted, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is the number that my answer should give me. And 12 over 36, if you prefer decimal, is 0.3, repeating. So this brings us to the general addition rule. When we do not have mutually exclusive events, meaning we have events that can happen at the same time, it's possible to roll 2 even numbers that add to a 6. I have a different addition rule. And that is that the probability of A or B is equal to the probability of A plus the probability of B minus their intersection, the probability of A and B. When we have overlapping events, we must subtract their overlap. So we don't do any double counts. So it happens to be that you can always use this equation for the addition rule, because if you have mutually exclusive events, A and the probability of A and B would just be 0. And so it would reduce to the probability of A plus the probability of B. it's good to keep this in mind. This is a common source of error for students. Okay, so just as a quick reminder to put that in writing, notice that if A and B are mutually exclusive, then the probability of A and B equals 0. And then you get what we discussed previously. All right, moving right along. Okay, we have another example. And by the way, everything we have from now on are examples to help us cement what we've learned, but we've covered all of our learning goals. So example 4, a card is selected from a random deck of 52 cards, and we have a deck of 52 cards pictured here. Determine the following if the following events are mutually exclusive, and then find their probabilities. So for A, we have the probability that a card is red or a queen. Now, we don't have color printers, so I'll just tell you that hearts, cards with hearts on them are red, and cards with diamonds on them are red. So the probability that you are red or queen, well, let's look for that. First of all, I already know that they're not mutually exclusive because there are 2 red queens. So not mutually exclusive. These events can occur at the same time. And then that tells me that I need to use this formula. Probability of red plus probability of queen minus the probability of a red queen. The probability that I'm red, well, there are 52 cards and half of them are hearts and diamonds. So the probability that you're red is 1/2. Plus the probability of queen, well, there are 4 queens in the deck. So the probability that you're a queen is 4 out of 52. Minus the probability that you are a red queen. 2 out of the 52 cards are red queens. Minus 2 out of 52. And I don't want to find common denominators, so I'm just going to plug all of this into my calculator. I have 1/2 plus 4 50-seconds plus 2, oh, sorry, not plus, minus the intersection 2 divided by 52. And that gives me 0.53. About 0.54, actually. And that's the probability of a red or a queen, 0.54. Okay, let's look at the next probability. Probability of ace or king. Now, there are 4 aces and there are 4 kings. So I also, there are 4 aces and 4 kings, and look, there's no overlap. Since there's no overlap, these are mutually exclusive. So these are mutually exclusive. These are mutually exclusive. Because there's no way for a card to be both an ace and a king. Since they're mutually exclusive, to find their probability of ace or king is just going to be the probability of ace plus the probability of king, which is 4 out of 52 plus 4 out of 52, which is 8 out of 52. And I put that in my calculator. And I get about 0.15. Next problem. Probability of a queen or an even number. Okay. Are these mutually exclusive? Well, I could be a queen, but I can't be a queen and an even number because my even numbers are numbers and queens aren't numbers. This is arguable, however, because some people would call queen 12, but we're not calling queen 12. So in this situation, queen or even number will be considered mutually exclusive. So the probability of queen plus probability of even. Well, there are 4 queens in the deck, so that's 4 out of 52. Plus, how many even numbers are there? 4, 8, 12, 16, 20. So 4 out of 52 plus 20 over 52, which is 24 out of 52, and which is about equal to 0.46. Okay, part D, probability that you have a black card or an odd number. We don't have color printing, so I'll show you. Black cards are the little clovers. Clovers and spades are black cards. And are these mutually exclusive? Well, these are not mutually exclusive. For example, you could be the 3 of clubs or the 3 of spades. So right away, I found an overlap. So not mutually exclusive. So I need to use my longer formula. And this is going to be the probability of a black card plus the probability of an odd card minus the probability of an odd black card, which is, I've got a 50-50 chance of getting black or red. So the probability of a black card is 1/2 plus the probability of an odd card. There's 3, 5, 7, 9. 4 times 4, there are 16 odd cards. 16 over 52, and I have to subtract their intersection. How many odd black cards are there? 3, let's see, 3, 5, 7, 9, 4 times 2. So minus 8 out of 52 equals, I'm going to use my calculator, 1 divided by 2 plus 16 divided by 52 minus 8 divided by 52, and that equals 0.65 approximately. Okay. Example 5, and then one example on the back, and then we will be done. Okay, example 5. Students in an urban school. No, there's no reason for the school to be urban. Students in a school were curious about how many children regularly eat breakfast. They conducted a survey asking, do you eat breakfast on a regular basis? All 595 students in the school responded to the survey, and the resulting data are shown in the two-way table below. Pay special attention to this two-way table, everybody, because one of our learning goals, one of the standards for the class, is that we can use two-way tables for probability. All right, so we have this table summarizing the results, and we have to use it to answer these questions. First question, if we select a student from the school at random, what is the probability that the student is A, female? Well, there are 595 students in the school, so the sample space has 595 elements. And there are 275 females, so the number of outcomes in the event is 275, and that probability is equal to 0.46. Okay, part B, someone who eats breakfast regularly. So, people who eat breakfast regularly. There are 300 students who eat breakfast regularly. 300 out of a total of 595 students. And that's about 0.5. Okay. A female who eats breakfast regularly. This is an intersection question. So in the table, it's the overlapping cell. This is an overlapping cell. Okay, so female who eats breakfast regularly. There are 110 such students. So that would be 110 over 595. And that equals approximately, put it in my calculator, 0.18. Okay, part D, a female or someone who eats breakfast regularly. For that, I use the general addition rule. So I have the probability that somebody is female plus the probability that they eat breakfast minus the probability that they are female and eat breakfast. And that equals, let's see, there are 275 females, 275 over 595 plus 300 students who eat breakfast, 300 over 595. And I overcounted the intersection, that's why I'm subtracting it. So minus 110 over 595, which equals putting it in my calculator, 0.78. Last page. Final example, just a little bit more practice using a two-way table. Okay, the hair and eye color of a group of women were measured, and the results are shown below. One of these women is randomly selected. What is the probability that A, she either has red hair or green eyes? So this is an or question, meaning I will use my general addition rule. And that's going to be the probability that of red hair plus the probability of green eyes minus the probability of red hair and green eyes. So the probability that she has red hair. Well, this table has not done the totals for us, which is super fun. We have to do it ourselves. So to find totals, you just add up the rows and columns. Okay. How many students have red hair? I'm adding 16 plus 7 plus 7 plus 7. That's 37. And I need the total to divide by, so I'm going to have to do all of these. Let's see. 66 plus 34 plus 29 plus 14, that's 143. 36 plus 9 plus 5 plus 2 is 52. 4 plus 64 plus 5 plus 8, that's 81. To find the total number of students, I can add those numbers up. 52 plus 143 plus 37 plus 81 is 313. So there are 313 students. And I also need to know the total number of students with green eyes, so I'll find this as well. 2 plus 14 plus 7 plus 8 is 31. Okay, now I can do this problem. So the probability that a randomly selected student has red hair, that's 37 out of 313. Plus the probability that a random student has green eyes, that's 31 out of 313. But there is an overlap in these scenarios. They are not mutually exclusive events because the intersection does not equal 0. I need to subtract the intersection, which is 7 over 313. And if I put all of that in my calculator, I get the probability that a student has red hair or green eyes, and it's 0.19. Now, part B says, what is the probability that somebody has red hair and green eyes? And we actually found it when we were doing this one. That's the probability that they have red hair and green eyes, which is the intersection 7 over 313. And that equals about 0.02. Okay. I hope you had a nice time doing these notes. Today, we learned the definition of mutually exclusive. We applied the general addition rule and the addition rule for mutually exclusive events. And we learned how to read two-way tables. See you next time. Bye, everybody.